Yeah.
Shall we start, sir?
Take over and ask Praveen ji to.
Yes. Dr. Praveen?
Yeah, we'll start, sir.
Yeah, please.
Thank you, sir.
Good morning, all. Today we have gathered here to commemorate 70 years of India's independence. The first module for this celebration is taught by Professor Kayal, the doyen of Indian seismology. It is a happy coincidence that IIG is also celebrating its golden jubilee. Marking and celebrating events is an invitation to ruminate and foresee. The Indian Institute of Geomagnetism and almost all the research organizations after the independence were given a fair share of mandate to work around the scientific of the country. India has been at the forefront in many, IIG has been at the forefront in many fields of geomagnetism and allied fields. It has come a long way and has also gone places. The mandate has been fulfilled to a large extent, but new ways and means to explore the world are being actively sought by IIG. This is the time to take stock of all the achievements and laurels, but it also will entail planning for the future. Course correction is an ongoing process and it will get a fillip by the wise words of a sage like Professor Kayal. Before I hand over the floor to Director Sir for his opening comments and introduction of the stalwart, I would like to make one request. I know there will be many queries, comments, questions through the course of this lecture. We have vibrant groups working in our own institute who are working in seismology. They will have a lot of queries and questions to ask of Professor Kayal. But it will not be prudent to disturb the speaker. It will be ungracious. But you definitely can write into the chat box your questions, which will be taken up after the lecture. Now I request Director Sir for his opening comments. Sir.
Thank you, Praveen. Namaskar, sir, and my colleagues. A very good morning to everyone. It's indeed my proud privilege today to be associated with the Amrit Utsav, Azadi Ka Amrit Utsav distinguished lecture series. I am doubly happy because this series, as the inaugural speaker, we have a very distinguished and accomplished seismologist of the nation in Professor J.R. Kayal, who incidentally also was very close. His date of birth is very close to the independence year. So it's a double delight to have Professor Kayal amidst us today. Professor Kayal has graduated from the Indian School of Mines and later went to the Victoria University at Wellington, New Zealand, and obtained a PhD in seismology. He was one of the earliest Commonwealth scholars who was exported abroad to bring home knowledge in the then nascent field of seismology, especially both observational and field seismology. After his graduation, he has had an initial stint with the Oil and Natural Gas Commission, which was a natural destination, and subsequently, the Geological Survey of India was fortunate to have him on its ranks since 1971. Dr. Kayal's first love and passion is seismology. It is no exaggeration if I mention that seismology in GSI is synonymous with Professor Kayal. It is Professor Kayal's vision foresight and his passionate understanding of the applications of seismology both in resource explorations and hazard that literally nudged GSI into establishing a full-fledged division in seismology, which was otherwise dominated by institutions like the National Geophysical Research Institute. It is also a very, I would say, a great coincidence that Dr. Kayal had a very able assistant by who goes by the name of Dr. Reena Day. This combination was literally, they gave a run for the money of other seismologists in the nation. Understanding the seismotectonics of the most complex geodynamic setting of India, that is the Northeast India, in very hard and harsh field conditions then was a real challenge. Dr. Kayal led his team so admirably that seismotectonics of Northeast India had a bearing and a stamp of Kayal's authority. His deep understanding and his continued association with several universities in Northeast India testify his fascination to this geodynamically challenging and complex region. Sir, I must confess that we are still struggling to comprehend the complex natural laboratory that is ongoing at one end and which has ceased perhaps at another end in that region. Their interaction, we always worry about two plate interactions, and one of the first geodynamic setting that comes to one's mind is the Japanese islands. But sir, your work has established what a stagnant plate and what a dynamic plate, when they interact together, what sort of seismotectonics are fashioned, what type of stress regimes would occur, what type of geophysical anomalies would persist both in time and space. Sir, it is your acumen and deep insight into the field of seismology, adopting state of the art technologies that took you across the globe. Your work has been very widely commended, appreciated, and recognized, by virtue of which you have been a visiting professor and a visiting scientist invited by several leading countries and institutions of the world, such as the GFZ, Geoforschungszentrum Potsdam, currently. You have also been closely associated with ICTP and have contributed to several national delegations to the EASPI, AGU, and IUGG. Sir, you continue to advise several national organizations such as the Ministry of Earth Sciences, CSIR, the presently named IIT Indian School of Mines, NGRI, Wadia Institute, NHPC, National Hydropower, and the Atomic Energy Regulatory Board. It is really amazing that in spite of the distractions of visiting several countries, especially your association with USGS, then New Zealand, Australia, then the University of Strasbourg in France, then several institutions in Germany. You have also been very kind with several Southeast Asian nations in imparting knowledge and also bringing them onto the seismological map of the nation. In spite of all these distractions, it is really amazing that you have authored over 150 scientific articles in peer-reviewed journals and contributed more than 200 research papers in conferences. I really do not know how you could manage your time um, for research, between research, the administrative work as the Deputy Director General of GSI, and your visits abroad. This only speaks volumes of your innate ability, your strength in dividing your time among most deserving partners for the progress of science. Dr. Kayal is also is the sole author of the book Micro-Earthquake Seismology and Seismotectonics of Southeast of South Asia, a publication that received wide acclaim across the globe, both by people who indulge in studies of the hazard and the structure of the Earth's interior. The nation has been grateful and recognized the services of Professor Kayal by awarding him the National Geoscience Award in the year 1994, and also the Indian Geophysical Union, I would say, has uh, what you call recognized itself by awarding the decennial award in the year 2010. Sir, it is with such wisdom, with such knowledge, uh, you stand today before us as a role model. Your humility and your down to earth approach to several geophysical problems are worth emulating. Sir, we are extremely fortunate and we are very much delighted to have you among us today, and we look forward to your sharing of your experience about the Northeast Indian region today. And we are once again very pleased that you are the first distinguished speaker in this distinguished lecture series. Professor Kayal, over to you, and thank you very much, sir.
Thank you, Dr. Ramesh, for your so kind introduction and so kind words and generous words of me. And I extend my very good morning to all participants, to my all fellow geophysicists across the country. And I thank Dr. Mala Bhagaiya for inviting me to this forum to share my little experience and knowledge on seismological investigations in Northeast India. So I straight away come to this topic and we try to see, just sum up some highlights of the investigations in this part of the country, which is one of the most vulnerable zone, earthquake risk zone in the country. So let me start from here. That the starting point of seismological investigations in the country was the devastating earthquake of 1897 in Ceylon, the great earthquake. And that earthquake was investigated by GSI, by R.D. Oldham, the then Director General of GSI. And that was the starting point when the first seismological instruments was installed in Calcutta in end of 1899. So you can say almost 1900. So since 1900, the seismological stations have been established, but it went very slowly. For such a big country, we had something like, you can see some, by 1905 after Kangra earthquake, 3 more were established in Agra, Hyderabad, and so on. Then by 1930 or 1960, it's only 15 observatories in the whole country. So really, so to say, unlike physics and other basic sciences, geophysics is young, much younger, and I think seismology is more young. It's hardly, in this country, we have started hardly 100 years, or maybe 100 years plus. And then, after devastating Kayal earthquake, we started the digital observatories since 1996. Today, we have something like 150, or the other day, MOES was telling 150 observatories around the whole country. And of course, with some clusters in Northwest Himalaya, which is run by Wadia Institute of Himalayan Geology. And another cluster here, which is used to be run by NGRI and NIST. Now I think everything, all data are now being, handled by NCS, National Seismological Center, which is now under Ministry of Earth Sciences. So it started with the IMD, but now NCS has come up, and which is now monitoring the whole country's seismicity with the broadband network of about 150 seismic stations. And those many stations are run by different organizations, including GSI, NGRI, and many other institutes. And those data go to NCS, and a comprehensive data center is made now in New Delhi in NCS, under NCS. Now, if we look at the recent data, recent earthquake seismicity map of India, now from here you can see how over the 71 million years, the Indian plate has moved, and it has now with head-on collision with the South Asian, here Eurasian plate. And this is the present topography of the Indian plate. Himalaya has come up due to head-on collision with the Eurasian plate over here. And along the Andaman, Nicobar, and Sumatra trench, the oceanic plate, Indian oceanic plate, is subducting. And this whole Indian continental plate is between two ridges, 90° east and 80° east ridges. And the Indian plate is moving from somewhere, Carlsberg ridge from here, the spreading ridge, and it is now on head-on collision with the Himalaya over here, and subduction tectonics over here at the trench region. Now, this is the seismicity map, where you can see the spreading ridge is also showing some seismicity, and all along the Himalayan collision zone, the seismicity is there, and it is in the Indo-Burma arc. It is a bit debatable, but there was a sea and there was subduction. Now the Indian plate is on with Burmese plate. It is now on head-on interaction, but this subducted Indian plate is still below the Indo-Burma ranges, means the earthquakes are still deeper here. So this Indo-Burma arc is connecting the Andaman Sumatra trench like this. So this is the seismicity all along the subduction zone, which is connected to the Indo-Burma Arc, which is also, we name it atypical subduction zone. This is not between oceanic plate and continental plate, but between continent plate. So we call it a atypical subduction. So we get earthquakes due to subduction tectonics in the eastern part of the Indian plate, and in the northern part of the Indian plate, we get all collision tectonic earthquakes. And within the intraplate region, we get the intraplate earthquakes. Those are infrequent, but sometimes they become fatal, like that of Kilari earthquake or Koyna earthquake. Even the Bhuj area is also in the category of intraplate earthquakes, and that earthquakes are also in here, very fatal here in Bhuj. So our two parts, Western India and Northeastern India are seismically very risk zone. And Himalaya, of course, is a very risk zone. And then the subduction zone earthquakes, and we had tsunami earthquake from here, from this zone. So this is the seismicity scenario of the Indian subcontinent plate. And when we examine the earthquakes across Indo-Burma ranges, you see the earthquakes are still dipping down to about 200 kilometers, 180 kilometers. So the dipping structure, the dipping seismic zone or venue zone is still is visible from the seismic activity. When you come to this Andaman subduction zone, this is a typical subduction zone earthquakes, and they go up to 360 or so. In Sumatra, the subduction zone or venue zone goes up to 400 or 450. But when you come to Sumatra, Java region here, the subduction structure, the venue zone or seismic zone goes down to 660 kilometers. So that's the general scenario of the, tectonic around the Indian plate, collision and subduction tectonics. We also have intraplate tectonics. We also have spreading zone seismicity over here. So now, how the instrumental seismology started? Because as I said, we had no instrument till 1899 or say 1900. So before that, the earthquakes are not instrumentally recorded in India, but even in the Western countries, the first observatory came in 1887. So we are lagging by about 10, 12 years. So this is the first observatory, first analog system was made by Ewing Pace and others. And before that, there was a first seismoscope came at 132 AD. So this was a Chinese scientist who made a seismoscope. Seismoscope means it records the timing of the earthquake. It has some, some dragon type of things, and due to the down motion, the dragon throws the ball like that. Due to the motion, the ball is dropped. So they get the timing of the earthquake, but there is no record. No record is recorded by this seismoscope. The first instrumental recording system came in 1887, and then by 90s, from the recorded earthquake, we found that the lower magnitude earthquakes goes by power law 10 times. Means if a magnitude 6 earthquake occurs once in a year, there will be some 10 earthquakes of magnitude 5, 100 magnitude 4, and 1,000 magnitude 3, like that. So it goes in 10 times. So then the micro earthquake seismology or micro earthquake instruments were developed. And then from analog system, the digital system came sometimes in 1990s. So this is how the seismological instruments develop. And these are the basic principles of seismometers. And these are the records, analog records by portable instruments. These are also analog records by tape seismograph. In New Zealand, I studied these. So you had the remote stations, you can put the tape recorder to record it, and the record can be read on the oscilloscope. You can also record them on the developer. By telemetric system, means different stations can be connected at central stations, So they're all analog systems, including telemetric system. But since 1990s, the digital system have come. These are the different type of seismometers and also a strong motion instruments here. And now we are recording digital records and 3 component records, vertical and 2 horizontal component. And you can see how nicely they are recorded and how nicely you can read them on computer. So things have, over 100 years, from no instrument to analog instrument, then to digital instruments. You see, in those days, from this type of, this is Alaska earthquake 1964. You can see how difficult it is to read these analog records. But those dedicated scientists, our grandparents or whatever you say, so those scientists, they examine every wriggle of this type of seismic, waves, and they came to this Earth's interior structure from such records, analog records, which is very difficult to read. The onset of different phases. Then digital systems have come. This is 2004 Sumatra earthquake, and this is record of something like 1 hour or so. These records are 2 hours, not 1 hour. So these records now you can see on the computer very, by zooming, every wriggle of the seismogram can be read very precisely, and you can understand the different discontinuities in the interior of the earth, and those are now studied with the modern instruments. So these are and you see with the analog system, the Gutenberg discontinuity between the mantle and the outer core was estimated 2,900 kilometers. And by this digital system, it is almost the same with plus minus 5 kilometers. So you can see how precisely those work have been done even by the analog system. And today we are in much advantageous situation with digital systems. Now, how do I, since it is for the, for many people from geophysics background, I mean from physics background, so I'm giving little bit of, understanding of the earthquake location and fault plane solution. Then we'll go over to Northeast India, the tectonics part. So in those days when there was no computer system, IMD even till other day, till 80s or so, the earthquakes are being located manual. And what is the physics behind it? Because if your earthquake is here, hypocenter at depth, and the projection on the surface is called epicenter, and suppose this is your station, observatory, then this distance is can be given by 8 times interval of S and P. That is by simple algebraic thing. You can find out if this is the distance, what time it will be taken by TP, means by P arrival, and what time it will be by say VP and D by VS. So you can just find out that this distance is given by 8 times of TS minus TP. And suppose this is your earthquake. So if you know the S minus P time, this interval, and if you know it at 4, 5 stations, then you can draw the arc. And that intersection of the arc is the epicenter. Once you know the epicenter, you can find out and the depth also can be found out from this, derivations, and you can find out the D, you can find out the, the X. So this is how the earthquake epicenter is to be located by graphical methods, by manual methods, and their approximate depth is to be estimated. But today with the computer system, we are now locating earthquakes with much precision by least square method, by then joint hypocenter method, by double difference method. These are all, a PhD topic itself, by itself, double difference, simultaneous inversion. So this is the routine method by multiple regression. If you know the arrival time, if you can have a velocity model, just assume start with, you can assume it. And then you can find out the location and depth, and you can also find out the magnitude. So this is the routine method, but for research type of activity, publications or work, more fine work, we need to do the station correction, because your stations, some stations are on the hard rock, some stations are on the soft rock or on sediments. So there will be station correction, and that you can estimate from this method. You can estimate the station correction, and you can apply those station correction and find the locations. But this double difference method is, you are taking the difference of the time between the two events, very nearby events, recorded by two stations. So that difference of time will be independent of the velocity error, because they are traveling almost the same structure, same path. So this is also another way of doing, precise locations. And this is, I think, best method. You are locating the earthquakes by inversion. At the same time, you are also, by inversion, you are estimating the velocity structure, 3D structure. So both the structure you can image and you can locate the earthquake. So simultaneous inversion is the state-of-the-art technique. And you can see an example here how this subducted, Pacific plate, high velocity plate is very much, well imaged, and this lower velocity red things, the lower velocity structure, in the continental side, in below the volcanoes and all things. So the Earth structure can be well imaged down to even the interior of the Earth. That I'm not going to that global tomography, but I'm just giving you a glimpse how the technology have developed over the years. Now you all know about magnitudes. There are, to start with, Richter 1935 was first. He was the first man, seismologist, who thought about this magnitude scale, because the size of the earthquake, you can go to the field and do the survey for damages, how much damages is there. So the damage is there, but what is the energy of that earthquake? For that, Richter first proposed this Richter scale, and this is on a very simple assumption. He designed this scale. It's a monograph. You can just nomogram. You can just know the S minus P time, the distance of that earthquake, as I explained just now, the S minus P time and the maximum amplitude. So this is your S minus P time, or distance of the earthquake, and this is your maximum amplitude of the earthquake that you read, and then you mark these 2 points, and you get the Richter magnitude from this scale. So this is how he gave, and it works very well. It works till today, and it is now with the invention of other magnitudes, from body waves and from the moment magnitude, other things. We found that MW is the most theoretically based, most stable magnitude, and this is more precise. But Richter magnitude is still popular, and it works very well. I think up to magnitude 6.5 or so, and beyond that it saturates. So I think more than magnitude 6.5 or 7, we can go for moment magnitude, but Richter works very well for lower magnitude earthquakes till today. And there are various scales here there, and then the intensity is the degree of damage. And the first intensity scale was proposed by Rossiforel, then modified Mercalli scale, Mercalli intensity. Then nowadays it is MSK scale. So this is just refinement after one after the other scale, and these are all descriptive scales. So you all know about heard about this magnitude and intensity. So these are the defined scales to measure that. Now, to understand earthquakes and tectonics, we need to understand also the fault plane solutions. So it was again based on this Reed's theory in 1910, and you see it was based on the observed earthquake deformation in San Andreas Fault, and you see if this is the fault and if this is the ground motion, the rock is deformed and then it breaks and rebounds. So with this situation, if you imagine another axis, like say a dot, and this is your fault axis over here, then you have got 4 quadrant, and you can expect ground motions like this for this type of movement, and you can expect dilatation, or that is P wave fast motion will be down, and in this zone it will be plus or up motion. So studying this ground motion from your seismograms, from your records, you can plot them by some technique. We call it, stereographic plot. It is a geological technique, and you can plot those fast motions, up motion and down motion, and you can divide them by 2 orthogonal planes to understand the focal mechanism. But here it is known that this is the fault and this is the movement. But if you do not know the fault, then either of the orthogonal plane can be a fault plane. So that you have to interpret, based on your knowledge, based on your judgment, based on the geology, based on the seismic section and all these things. Then came, with the digital system, then came the moment tensor solution. So you can study the waveforms, and you can come out with the, by waveform immersion, you can come out with the solutions like this. So you can find from the fast motion data. You can also estimate. Nowadays, people prefer the waveform inversion technique from the waveform data, from the digital data. But before that, it was all analog data, and fast motion data were giving us the ball pen solutions. But both works equally well. And this is the dynamics of faulting. If your compressional stress is horizontal and the tensional stress is vertical, and the intermediate stress, 3 principal stresses, intermediate stress is also horizontal. In that case, means when compression is horizontal, you get fast faulting. And this is the symbolic presentation, means that this part is compressional zone, means the up motion of the P waves. And for the normal faulting situation, you have tensional stress, horizontal, and where your directional zone is in the middle. And for the style-step solution, when you have both p-axis and t-axis is horizontal, you are under a shear stress, then you get this type of, solution. But there can be mixed. It can be pure thrust, or it can be with some component like this. It can be pure normal. It can be with some component. So like that, you can have various types of fault solutions to interpret in terms of your tectonics in that study area. So now I think I am coming to the Northeast region, and what we understand today about the regional seismicity in Northeast India. Now this is one of the most earlier study in 90s, where we use the USGS data, or ISC data rather, ISC data, and we studied that this Indo-Burma range, as you have seen, is intensely active, then the Himalayan collision zone, and then the Shillong Plateau or intraplate zone. This is intraplate, means this is away from the boundary. If it is more than 100 kilometers away from the boundary, boundary zone, plate boundary zone, then we call it an intraplate zone. So intraplate zone earthquakes, then the syntaxis zone earthquakes, means where the Himalayan collision zone and the Indo-Burma subduction zone are meeting. This zone is called syntaxis zone. So that is one tectonic block over here. Collision zone, one tectonic block. Intraplate Assam Valley, that Mikir Hills and Shillong Plateau and Assam Valley is one intraplate zone. There is Bengal Basin, another intraplate zone. So, intraplate zone. So there are different tectonic blocks. And when we examine the earth sections, is across the eastern Himalaya, we found the earthquakes are, up to 60 kilometers, 70 kilometers, they are confined. And it is unlike Western Himalaya. In Western Himalaya, earthquakes are down to mostly 20 to 25 kilometers. But in Eastern Himalaya, they are deeper, down to 60, 70 kilometers. But they are in the collision zone, there is no subduction structure. But as you come across Shillong Plateau and in the Burma ranges, then you find a very, defined seismic zone or Benioff zone you can find. And this interface we demarcated from the normal faulting to thrust faulting region. So, and when you come to Bengal Basin and Indo-Burma ranges, this is the structure. Bengal Basin is less active, and Indo-Burma ranges, below Indo-Burma ranges, Indian plate is subducting, and there is seismic activity. So this structure we again studied. And then another point, when we took this section along the Indo-Burma ranges, we found that the earthquakes are deeper from south to north. Earthquakes are deeper down to say 150, 180 kilometers. But beyond 26-degree latitude, the earthquakes are shallower. Means what we want to say that beyond 26-degree latitude to the north, beyond 26-degree latitude, the subduction ceases and the collision tectonics take over. This is the syntax issue. So that is one interesting observation. Then we try to study these structures with the gravity anomaly published by Varman and Mukhopadhyay, and it was matching with our this structure and with this sedimentary thickness in the Indo-Burma ranges. So this is our preliminary study in 1990s. Then most recently we have studied with the more precise located earthquakes, and that is EHB located earthquakes. In the ISC catalog, we will find that there is a EHB catalog which is better estimated depth those earthquakes. So EHB catalog is about 3 years lagging from the ISC catalog. ISC catalog you can almost get the current, and USGS is within half an hour or so. So this also shows that you can see that in the syntaxis zone, we had the 1950 earthquake. I will not go into details about the Eastern Himalaya today. I will be concentrating in this part of the country because it is too big, it will be too big. But let me tell you that in the syntaxis zone, our first great earthquake was 1897. And the second great earthquake was in 1950. 1950 earthquake occurred in the syntaxis zone, and there are a debate that it occurred by thrust faulting, it occurred by strike slip faulting, but the waveform inversion or those analog records were converted to digital waveform, and then they were studied by moment and solution, and that gives strike slip mechanism. So that is, I think, preferable solution for this, because there are all this structure like this northwest southeast tending fault are here, and they are matching with the fault plane over here. And then the 1897 great earthquake occurred at the Shillong Plateau boundary over here, and this is the fault plane solutions. And there is another earthquake zone that is called Kopili fault, which has fragmented the Shillong Plateau. The Shillong Plateau is a part of the Indian Shield, and again it is fragmented by a Kopili fault. One is called Mikir Hills, Mikir Plateau, and this is called Shillong Plateau. So this Shillong Plateau, this Kopili fault, which is from this end to up to Himalaya, it is transgressing. We believe that the Kopili fault was the causative fault for the 2009 Bhutan earthquake over here. That is, I'm not going into details into that. So this, what I want to convey you, that the Kopili fault is a long fault, about 300 meter long fault, and about 50 meter wide zone, seismic zone over here we find. So this is one, earthquake zone. The Shillong Plateau itself one earthquake zone, and it has already produced a great earthquake and the syntaxis zone. And this zone, you can see there are some 20 large earthquakes. All those circles, bigger circles are magnitude 7 and above. These two stars are great earthquakes. And all the red, you can see that there are about 5 large earthquakes, means 7 and above, in this zone. One is Dhubri, one is at the boundary, Mymensingh, one is 1869 in Assam, another 1943 in Assam. So there are some 5 large earthquakes, and then Bengal Basin earthquake over here, 1918 earthquake, Sylhet earthquake. We call it Simongol earthquake. So these are the intraplate earthquakes, means they're away from the collision zone or subduction zone. So there are quite a few intraplate earthquakes. One is great earthquake, one of them, and of course the syntaxis zone great earthquake, and this Indo-Burma subduction zone is producing many, about 2 dozens of large earthquakes over 100 years or so. So this is the scenario, and you can see that our sections also show similar things what we have observed in 1990s, and this subduction zone or Benioff zone, and then this also along the sky, and beyond 23 degrees latitude, the earthquakes are shallow, and the 1950 earthquake occurred over here. So that is our, just general regional seismicity observation. Now, this is another interesting observation done by Rao and Kalpana in GRI. And they found that in the Indo-Burma ranges, there are two types of major, we can divide into two types of earthquakes. One is thrust faulting. Of course, there are some, components, seismic component, and there are thrust faulting earthquakes, means dominated thrust faulting and dominated normal faulting earthquakes, or normal faulting and seismic component. And they found that the upper part of this Indian plate means down to 90 kilometer depth. This upper part of the plate, due to bending and tensional stress, is dominant. So when the tensional stress is dominant, as I said, you get normal faulting. So normal faulting normal faulting earthquakes are mostly on the upper part of the plate, and in the deeper part of the plate, the earthquakes are mostly of thrust faulting. So this is a good study to understand that the subduction zone earthquakes, how it is behaving with the subducted plate. Now, this another study we have made very recently. It has come in the tectonics paper, and it was first observed by Kaulakov, our Russian experts, in our collaboration. He first published the 2011 paper in JGR, where he has given this, this tomography picture at a depth of 100 kilometers in this Northeast India region. He took the global earthquake, teleseismic earthquake, and he has published this map. And then it is the section across, say, intraplate and subducted plate over here. So here he has found that the subduction, the subducted high velocity zone is continuing down to something like 400 or so, 450 kilometers. So that means it was a subducted plate in the geological past, and now that high velocity zone or that subducted part is tear off here, and the upper part up to 200 kilometers is now still generating earthquakes due to plate interaction. So there was subduction, and the subducted high velocity structure is imaged by seismic tomography. Now, in our collaboration with the Indo-Russian collaboration, we studied the regional earthquakes. Means we have taken the regional data over here, our Indian National Network data mostly, and some data from the other sources. So these data, now we have studied the regional structure, and he found that what he found by his teleseismic events, our study confined up to 100 kilometer depth, and he has gone up to something like 500 or 600 kilometer depth. So this part we have again done the detailed study. We found that our detailed study is fairly matching with his earlier, global seismic tomography, this teleseismic tomography picture. So this is our observation, that the observation is saying that the high velocity structure is still visible, and the upper structure up to 100 kilometer structure is much detailed information we have imaged by our collaboration. So I think now I should come to this part, which is of our interest, what we understand about the seismotectonics of Northeast India. So you see, as I said, that we have collision zone earthquakes, interplate earthquakes, and they are 1950, as I already explained, 1950, and MW 8.4. The initial magnitude was MS, surface wave magnitude. Now it is revised to moment magnitude by Aravezes and Douglas. So it is 8.4. That is the highest magnitude earthquake in the Himalayan region. And then Bhutan earthquake, you all know about it, 2009, and then 2011 Sikkim earthquake. I'm not going into details into this again. Then the Indo-Burma subduction zone earthquakes, recent earthquakes of 1988, 2015, and 2016, and recent Manipur earthquake, rather Mizoram earthquakes in 2020. Those red things I will explain, not this one, of course. These Mizoram earthquakes I will explain in more detail. Then the intraplate earthquakes. the Assam along the Kopili fault. As I already said, that 1869, 7.4, again MW revised magnitude. It was 7.6 earlier. Now it is 7.4. And Assam earthquake 1943, 7.2. These two red circles are the Kopili fault earthquakes. And recent Manipur earthquake is also possibly at the Kopili fault, extended Kopili fault over here. I will explain that. Then we have Silang Plateau earthquake. We have 1897 earthquake, 8.4. It was again MS 8.6. Now it is revised to 8.1 moment magnitude. Then Dhubri earthquake, 1930, 7.1. Then Bengal Basin earthquake in the interpret zone, that is Simongal and Mymensingh, 2 earthquakes. Then the Tripura fault belt or basin is part of Bengal Basin also in the western part. There are 2 earthquakes, 1950 5.9 and 2017 5.5. Maybe these most recent earthquakes I will give you some seismotectonics, but as a whole I have given you the geodynamics of this whole region as collision, as subduction, as intraplate, and then this transverse strike slip mechanism of the earthquakes over here, and this Bengal Basin earthquakes. Let me see if I get time. So intraplate earthquakes, past intraplate earthquakes, a quick review I am giving. That is 1897 great earthquake, Shillong earthquake. This earthquake occurred over here. And if you can see, this is the Dauki fault we call it, which is separating the Shillong Plateau and the Bengal Basin. This is thick sediments region, deltaic sediments, and this is the Archean rocks that Indian Craton. And again, within the Shillong Plateau, there is a fault. We call it, the geologists have marked it as a Dapsi thrust, which is extension of the you can say of the Dauki fault over here. So that Dapsi thrust is separating the Shillong Plateau and the tertiary sediment within Shillong Plateau. And the Dauki fault is separating the Shillong Plateau as a whole and the Bengal Basin. And this is the Kopili fault, which is separating the Shillong Plateau and the Mikeri. And this zone is also seismically much active. And these are the recent earthquakes: 2016 Manipur, 2017 Tripura, and this, of course, I have already discussed. Now, this earthquake, Oldham gave a intensity map like this. You can see a hat type of contour map is here, and it was given something like 10 to 11, modified Mercalli scale that was given by Richter from Oldham. But this intensity map is again revised by recently revised, and it is also giving something like about 10 maximum intensity. And of course, it is widely felt beyond 1,000 kilometers. It is giving intensity of the order of 5 or 4. So it is widely felt. So this is the Oldham's observations, and this is from his data. It is again digitized and the modified intensity map is made. But what is important message here is that Oldham observed that the boulders were thrown into the sky and they were displaced, and that displaced boulders he has shown over here from this part to this part, it is displaced. And he reported that the ground acceleration of this earthquake must be 1g, no less than 1g. Otherwise, the boulder cannot be thrown into the sky. So that time we had no what to talk about strong motion instruments, accelerograms. We had no seismograph also to have seismogram. So his estimate today, his reported estimate of 1g ground motion is today highly appreciated by the modern seismologists. So that was his observations, and he gave a ground acceleration of 1g. And if you see that, the across Shillong Plateau and Indo-Burma ranges, that structure, the 1897 earthquake occurring here, and the pad boundary zone is somewhere here. Pad is started flexing, bending here. So this is a 1897 great earthquake at a depth of something like 25 or kilometers or so. But Oldham also again reported that this could be a thrust faulting earthquakes by some north dipping thrust fault. And we found that the Dapsi thrust from our microearthquake surveys in 90s, it was published in BSSA. We also supported that it could be a thrust faulting earthquake, and that was Dapsi thrust, because all the earthquakes in Sri Lanka to the north of Dapsi, and it was following the Dapsi thrust deep. So, but in 2001, a new model is given by Bilham in England, a pop-up tectonic model. Though this model was first proposed, rather hypothesized by some NGRI group of scientists like P.C. Rao and others, they said that because Shillong Plateau is rising up, there's no doubt about that, over 100 years from geodetic and GPS data, and recently the GPS data. So rising up of the Shillong Plateau is by pop-up tectonics, was first proposed by an NGRI group of scientists, and they said that they know the Dauki Fault, the Dhobri Fault, the Kopili Fault, and all this, and Brahmaputra Fault over here, which geologists say the Brahmaputra River is a Brahmaputra Fault, the east-west segment here. So Shillong Plateau is bounded by these 4 types of tectonic structures, and Shillong Plateau rising up. But Bilham gave they hypothesized. But Bilham gave a quantitative model saying that the Shillong Plateau is popping up between the Dauki Fault and the south being Oldham. They gave a name Oldham Fault from their GPS data and from the ground, mechanism, and they gave a quantitative model and gave a name a fault, Oldham Fault, at the boundary of the Shillong Plateau and Assam Valley. Over here, this line, red line, if you can see that this is the earthquake and this is the red line. So they gave a name, proposed a Oldham Fault. So that was the proposed model, or rather quantitative model. It was published in Nature. So that gave a huge debate and hue and cry, and geologists, GSI geologists do not believe there is no such surface fault and all that things. So we try to examine the broadband, recorded instruments, recorded earthquakes. There was a broadband network in those times. Something like 60, 70 broadband stations were running by NIST. And in this area, there are some 25 or 35 stations. These blue triangles, you see, broadband stations. So these were very well located earthquakes by broadband stations. And we, under Indo-Russian collaboration, we tried to examine these Shillong Plateau earthquakes, this rectangle Shillong Plateau earthquakes, and this Kopili Fault earthquake, this rectangle. We have taken section across and along also. So you can see that Shillong Plateau earthquakes are mostly of thrust faulting, and Kopili Fault earthquakes are mostly of strike slip and normal faulting. So this is observation, and then we have examined the sections. If you see the sections, you see that the time is running so fast, so I have to go also fast. So this, you can see the sections of the earthquakes, and some fault plane solutions of the higher magnitude earthquakes, magnitude 3.5 and above. We found that the fault plane solutions also matching with the two faults, south dipping and north dipping. But this north dipping faults, I think Dapsi thrust is more active now, and south dipping, whether it is Oldham Fault or geologist Brahmaputra Fault, we cannot resolve. But there is some, some structure over here, whether it is, you call it Oldham Fault or Brahmaputra Fault. The pop-up tectonics between two boundary faults is also evident from the seismic data. And also along the Kopili Fault, if you see, there are two structures, upper crustal earthquakes along the Kopili Fault, and lower crustal earthquakes. And these red stars are all felt earthquakes, magnitude 5 and above. Some are 6 also. And across the Kopili Fault, you can see the fault geometry. It is like this. And earthquakes are down to about 50 kilometers in the Kopili Fault. There are some shallow earthquakes in the upper crust, but down to crust mantle boundary, there are also earthquakes. So this is the geometry of the Kopili Fault, which is about 300 kilometers long and about 50 kilometer wide zone. And this is one of the most vulnerable zone for a large earthquake. Already experienced 2 large earthquakes in this zone. Now, one of my PhD students, he did study by B-value mapping and fractal mapping. And these mapping also give us, the Shillong Plateau pop-up structure and the Kopili Fault, big transverse structure, both in the p-value mapping and factor mapping. And the seismic tomography also give us very heterogeneous structure at 10 kilometer depth. Then at 20 kilometer depth, we find that Kopili Fault is still going there, and up to 30 kilometer depth, Kopili Fault is still there, and the Shillong Plateau is high velocity, and Bengal Basin low velocity up to 20 kilometer. Means the sediment depth up to 18-20 kilometer is there. But as you come to 30 kilometer depth, the Kopili Fault is still visible. Shillong Plateau is taking up the model velocity, and Bengal Basin also model velocity. But at a depth of 40 kilometers, you can see just at the end of the Kopili Fault, there is a high velocity structure. And we presume that this high velocity structure at the end of the Kopili Fault is the stress concentrator for generating earthquakes by triggering the Kopili Fault zone. So this is our study of the Shillong Plateau seismic zonic zone and Kopili Fault seismic zonic zone. Now let me quickly, maybe in 5 minutes, I try to finish. Now, these are the most recent earthquakes. Many of you may be interested to know about the what happened with these earthquakes. Manipur 16, Tripura earthquake 17, Mizoram earthquake. Of course, Mizoram is not a single earthquake. There are some swarm type of earthquakes. 8 earthquakes, felt earthquakes in 2020, and and Mizoram was very panicked. And Assam earthquake. Now Mizoram is making a good network there. Now the Assam earthquake. Most recently, 2021, in this year, in April. Very quickly, I will show you what happened to the 2016 Manipur. This is the Manipur. And these are the, eastern boundary thrust, and this is, CMF fault. This is the Kaladani fault, like that. And this is the Sagaing fault, which is, strike slip fault, and it is joining to the syntaxis zone over here. This is Kopili fault. This is Dauki fault, like that. And Manipur earthquake occurred here. And first, I think both the papers came in the same year, it's supposed. Galot and Tundu, from their GPS study, they said that the CMF fault, that is Chandrapur Mao fault, local name. This is their structure. They have given the model, the subduction structure below in the Burma ranges. And this is the CMF fault. And the eastern boundary first is some fault is here. And they say that it could be that CMF fault is the positive fault for this earthquake, which occurred here to the other side of the so-called CMF. But Singh and others, AP Singh and his group, they published in BSSA, they say that the rupture propagation along the Kopili fault and aftershocks also along the Kopili fault, they interpreted the Kopili fault is the seismogenic fault. And I prefer this interpretation because the fault plane solution here, you can see this nodal plane, which is, northwest, southeast, this nodal plane is matching with this fault plane, and also the deep is also matching with the fault. So we presume that, rather we find that the 2016 earthquake is a product of the Kopili fault earthquake at the extreme northeast point at the junction of the, say, this CMF and the Kopili fault. And fault interactions are always the vulnerable zone for large earthquakes. The same thing happened for the Bhutan earthquake over here, which is transgressing into the Himalaya, and the Bhutan earthquake occurred at the northern end of the Kopili fault. And this is the Tripura earthquake. Tripura earthquake, it is here in 2017 earthquake and 1950 earthquake, in the almost at the Bengal Basin part, of course. And this is some liquefaction picture. And one of my students from NIT Agartala, he did the liquefaction potential map. So based on SPT data and other things. And again, in that model, you can see that this is the Tripura earthquake, which is this one, black one here. So we have again replotted this Mizoram earthquake and the Tripura earthquake and the Manipur earthquake. And in this model, you can see that the Manipur earthquake is somewhere here, means in the interface zone, and the Manipur and the Tripura earthquake over here. Sorry, this is Manipur earthquake, red one, and this is Tripura earthquake. So Tripura earthquake is very much a intraplate basin earthquake, and This is the Manipur earthquake, which we already interpreted, preferably interpreted for the, generated by Kopili fault. And other Mizoram earthquakes, which occurred very recently, I am coming to that, they are all within this IBW, Indo-Burma wedge. And this is that, Mizoram earthquake. About 8 earthquakes occurred. These are all magnitude 5.3 to 5.9, and they occurred in this wedge, in this Indo-Burma wedge. And this is very well understandable that they are the subduction earthquakes, but at shallower depth. So this is what is about the Mizoram earthquake swarm. And we also studied this swarm, how this suddenly this earthquake, so many earthquakes. So we took this rectangular block and we studied magnitude 5 and above, because in the catalog they say, though they claim that 4.5 is a threshold magnitude, but we have taken 5 and above for the, at least for the earlier catalogs. So the 5 and above we have taken, and we found that the magnitude 5 and above earthquakes occurred, saying average about 5 or 6 earthquakes every 5 years. So this is from 1965, because 1964 first world-wide seismograph station network was established, and one station was in Shillong also, in Shillong Observatory. So this is one of the stations which was, run by USGS. So we have taken data from 1964, and every 5 years we have studied, and we find that in 2015, 2020, the average rate of 5 to 6 earthquakes, means 95 and above, has gone up to 20. So this is some sort of swarm, and such swarm is normally found before a large earthquake. So there could be a large earthquake in the Burma ranges is not a surprise. Now this is the Assam earthquake, that Sonitpur Assam earthquake, April 2001. And this earthquake, again, as I said, this earthquake occurred here. This is the Kopili fault, these black lines, and this rectangle we have taken to show all the earthquake sections along this strike, and this is across Shillong Plateau and Kopili fault, another sections. So you can see that Kopili fault earthquake, and this is the solutions, the CMT solution, and that we have made from our side. Also, it is also published by CMT in the IC catalog. So and these are the aftershocks. So you can see that Kopili fault, there are many felt earthquakes, and 6.1 earthquake also occurred on the Kopili fault. And if you see the sections along the Kopili fault, you can see just below the Kopili fault, so many earthquakes, and this is along from this end, and this is 2016 Manipur earthquake. From this year, this one 2016, and this one I think 1869. So from this end to that end up to Bhutan, it is transgressing. And 2009 earthquake, we also interpreted due to Kopili fault. Now across the Shillong Plateau and Kopili fault, you can see this is 1897 great earthquake origin over here, and the recent earthquakes in the Kopili fault. And this is the reds are the 2006, 2021, 6.1 and aftershocks. So this is the fault geometry. So Kopili fault is another seismic zone for large earthquakes, and we have already discussed Shillong Plateau is definitely a very big earthquake source zone, and these are some evidences of the intensity of the order of 5 or 6 for this Assam earthquake, and some spinning water, some ground deformation, some building tilt, and some liquefaction also occur. Now, how we can go for the earthquake disaster, because we have understood the source zones, as I already mentioned, but then what we can do about the society, how we can mitigate the disaster. So there are 3 ways, apparently to me. That one is earthquake prediction and forecast, which we should say till date no. Though you say there was an earthquake prediction in 1975 in Haicheng, yes, that was I think the only one earthquake predicted successfully. The story is a bit different. The geophysical precursor study was started, in 70s, and 1975 earthquake was well recorded in geophysical, in precursor studies. But the prediction committee did not predict the earthquakes. They were in dilemma. But what this earthquake will occur, nothing is known. Some precursor around is there. But one fine morning, they found that the all, rats and snakes, all underground, insects, everything in the full of the roads on the Haicheng city. Then the prediction committee, announced to vacate the houses. They vacated houses. They came into the open ground, and with the tent they lived. And within 24 hours, overnight, they lived in the tent, and then within 24 hours, next day, the earthquake occurred. So that was the only successful, you can say, of practical use. It was, and lives were saved, but properties could not be saved. Whole city was demolished. Same China, in 1976, Tangshan earthquake was totally destroyed, and something like 80,000 people were killed. So prediction, but until the other day, I think by sometime in 2009 or 10, I went to China on an earthquake prediction conference. The Chinese, they don't give up. They say, we don't give up. We will predict earthquake. So they have taken it as challenge. And about forecast, I think there is one, you can say, successful story. I'll tell you that. But we cannot say with time, space, and magnitude the prediction or forecast. Forecast is something like, 1 month, 2 months, and we will vacate the city for 2 months. So I think the answer is no, till date. Maybe one day, your artificial intelligence can do, but we are unable to do so far. Then identification of active fault and source zone. Yes, I have already shown you how we can identify that. And seismic hazard microdiscussion. Yes, we can produce that map for you, for the society. But they have to use it. There has to be public awareness. So these are the, I think, answers to mitigate the earthquake disaster. Yes, we did some earthquake precursor research. I'll go very quickly because this is itself a 1 hour lecture. So I'll just tell you that there are, by B-value, by PO residuals, by Gupta and Guha, and by seismic gap, by Khatri and others. Then based on these, we started an experiment from GSI in Shillong, and we found that, yes, there is some resistivity precursors before the Kachar earthquake of 1984, 5.8 or 6 magnitude earthquakes. So there was resistivity precursor, there was seismicity precursor, there was gravity precursor in over here in Shillong Plateau and Assam Valley. Another example, this is from Sikkim. There was a gravity change, and there was a seismicity rate change, and there was VP by VS change. So all these things are good for understanding the earthquake precursor or good for publication papers, but I don't think we could predict, or we predicted this earthquake. After the earthquake, we have tried to correlate, we have tried to understand. So now the MPGO MOES at that time DST took about this decision that there should be multi-parameter instead of this type of piecemeal work. Let there be multi-parameter observatory for earthquake prediction. I think one was also proposed for Shillong. I don't know what happened to that, but this one MPGO has come up now first came up in Guttu in Himalaya by Wadia Institute of Himalayan Geology. The other one in Andaman, I suppose, and one has come in 2015 in Tezpur under NEIST. This is that observatory. And this is a story, possibly you all know. This was by Gupta and Singh in 1986. They published a paper and they found some precursor swarm. Means in different time interval in the same space, some 3 degree by 3 degree area. With time, they found that this is the normal seismicity, and then it has swarm, and then there's a quiet area, a quiet seismic quiet period, and then they presume that based on Evison's swarm hypothesis. Evison happened to be my PhD guide, and based on that hypothesis, in 1886, rather 88, sorry. Oh, this is the 88 earthquake. Yes, 1986, they published the paper in Technophysics. Of course, with the area, this area means 3 degree by 3 degree in Hindu-Burma range. Hindu-Burma area somewhere in Manipur, near Manipur, means beyond Manipur to the further east. And they say within 2 or 3 years, a large earthquake is going to occur. They gave approximate magnitude 7. It was almost a quantitative, forecast, but they gave a time of 2 to 3 years. So it was 86 publications. Then 1988, the earthquake occurred. And 1989 in paper, they claimed, which is genuine, they claimed that their forecast has come true. But for the society, how it can benefit? The society, how can you live? Can you leave your city, Shillong city, for 2 months, for 2 years? So it is for understanding the earthquakes. I think it's good enough for studying precursors, but I think ultimately help us the microgeneration map. I think I have, yes. So I told you that the other option is large earthquakes, identification of larger earthquake source zones. So we have found that for you. Even the paleoseismological observations, paleoseismic study was done by some NGRI group, Sukija and others. And they found that in the 1897 Shillong earthquake, that, the Dudhnoi region, they found that the seismite, and they make trench and they find the seismite. Seismite means the liquefied, the liquefied mud is now turned into a stone, means over 10,000 of years. So these they have found, and they found 3 sequences, and they said they found that the great earthquake recurrence time in Shillong region is of the order of 500 years. But I think large earthquakes, strong earthquakes may occur, that recurrence time is not that much. So this is the paleoseismological evidences of great earthquakes in Shillong Plateau in the past, some 1,000 years and 1,500 years. And also along the Kopili Fault, another group of NGRI, Devendra Kumar, and they have studied the seismite in the Kopili Fault zone, and their recurrence time is of the order of 100 years. So 1943 is the last large earthquake in Kopili Fault zone. So I say whether 2021 6.1 earthquake is a wake-up call for the Kopili Fault large earthquake, because it's almost now 80 years. So Kopili Fault is vulnerable, but we can go up to this much. This is the risk zone. This is the active fault zone. This is the most vulnerable. All these things we can tell you, but ultimate solution, I suppose, it is with the people. We can also give you the microgeneration risk map. That it is again another separate lecture for 1 hour. But I can just tell you that if your structure is on the hard rock, basement rock, the structure survives. But if the same structure, same material, if it is on the on a surface which is below sediments, so that earthquake wave will be amplified, and this will damage the structure. So it is the site response which matters. So though you have a seismic zonation map, the whole area is risk region. But again, within this risk region, if you make similar buildings with same material, same engineer, then all the buildings will not collapse. Some buildings will collapse, some buildings will not. So that is because of the site response, site effect. So we can do the site response studies. We can do the basement, bedrock studies by geophysical methods. We can do the site amplification study, and at what frequency the site is amplified. That everything we can do, and then the landslide and other liquefaction potential. All this information can be plotted on GSI platform, and we have come out with the hazard map, and this is the risk map. This map, you understand the hazard into the vulnerability means we have also studied the population over here, and we have given this seismic hazard map for the Guwahati city. It was a NGRI GSI effort. at that time I was in GSI, so it is sometime in 2004 or 2005. So this is the scenario of the our understanding of earthquakes and how to save lives. So microgeneration map has to be implemented by the by the engineers. And the other day, what lessons we take? The Kobe earthquake. This is the Kobe earthquake. You can see a textbook type of thrust faulting, and this is in the field. I visited this site, and they have kept it, preserved it as a museum. This thrust faulting, situation, how the Kobe fault, Kobe earthquake, was generated, and even the nearby house where it was fully destructed, that also has been preserved as a museum. So this is how they carry the, lessons for the next generation. Even they have, they stimulate the earthquake disaster and give a fantastic video show. So this is how they take the lessons, and their observation that before 1980, the houses were not seismically designed, but after 90, all the earthquakes are seismically designed. So before 90, all houses, they are bound to retrofit. This is the ERI, Earthquake Research Institute in University of Tokyo. I was there for some time, and the old building here and the new building just opposite to it. So the old building is now retrofitted. You can see the crossbar if you can see my arrow. So this is retrofitted. So any building before 1980 in Japan are retrofitted. And any building and every building after 1980, they are all seismically designed. This ERI multi-story high-rise building is standing on bush. The building will swing but not collapse. And I experienced that also there. But what happened to Bhuj earthquake? After Bhuj earthquake, the 7.7 earthquake Bhuj destroyed everything there. You all know about it. But then the new Bhuj city has come, and one of my good friend, colleague, Dr. Pandey, Prof. Pandey, he was telling that in the new Bhuj city, Bhuj town, the buildings are also made on the fault. So this is how we take the lessons. And the other day, Jim Murray was telling that, the 2011 9.1 mega earthquake, the ground shaking did not kill the people because their engineers did a good job. The building collapse did not kill the people. It was the tsunami, unexpected, very high tsunami killed the people. So this is how Japan lives with the earthquakes, and they take the lessons, but we don't. I think this is my last slide. The warning system is another thing, and we had no warning system, earthquake tsunami warning system. Now we have it in Hyderabad, and this is physics. Is that you telemetrically get the immediate real-time data, and immediately you estimate the earthquake magnitude and location, and you say if it is in the sea and it occurred by thrust faulting, you say tsunami is coming. And you can see how tsunami takes quite a appreciable time for us to reach, but we had no system that time. But now it is predictable. Predictable means it can be warning, not predictable. It can be one. It can be one, and we have got enough time. Unlike Japan, they don't have hardly 20 minutes, 30 minutes time, but even they are successful in that time. And I think similar system will be there for the earthquake warning system. That is, when an earthquake occurred, suppose it occurred in the Himalaya, and the P wave is already recorded in the stations in Delhi, say, and it will immediately find and the earthquake magnitude and the location also. And then if it is 200, 300 kilometers away from the epicenter, suppose Delhi city and earthquake occurred in the Himalaya zone, then you have got some 30 to 40 seconds time. So that you can say that now the damaging wave is coming, but that cannot, I don't think practically it will be very useful for saving the people, but it is normally in Japan, it is used for emergency purposes, emergency shutdown of the powerhouses or bullet train. So it is very effective, and Japan is already implemented, it has implemented for the last 15, 20 years. And India is also thinking about this earthquake warning system. And tsunami warning system, of course, it is working well, and they are doing good job. I think I have completed my lecture. So thank you all for your patience. I have taken long time, and sorry to, little late, and thank you all for your patience hearing. I'll be glad to take up any question. Thank you all.
Thank you, sir. Thank you, Professor Kayal, for
Thank
the
you so much. Thank you. It's my pleasure. Thank you.
Yeah, Malaji, please.
Thank you, sir. Thank you very much, sir, for the wonderful talk. As always, the talk was full of knowledge, and it is always a treat to listen your talk, sir. Thank you. I am presently sitting at Shillong Plateau, so I could literally visualize the tectonic settings and seismic scenario around. And since our focus is on Northeast Indian region and aim is to delineate the earthquake precursors in Earth atmosphere ionosphere system, I'm sure that the knowledge which you have shared with us today will surely benefit me and my colleagues in our future studies. In recent past, IIG has made certain progress towards tsunami early warning system from the ionosphere, and hoping that it may be useful for real-time early warning for tsunamis. I think the talk is open for discussion now. Any question one can ask through WebEx, or you can type in YouTube chat box also. Questions?
Please, Shantanu. Yeah.
Yes.
Yeah, hello.
Yes.
Yeah, hello.
Yes, yes,
Thanks for,
Shantanu.
yeah,
The
thanks,
questioner may please identify and then ask the question. Identify himself, then ask the question.
This is Shantanu Pandey from Shillong, SGRC. Thanks, Professor Kayal, for this very informative and very informative presentation. So I have a few questions. So since I got so many information, just bear with me with a couple of questions.
Yes, you can
all,
email me also. Yes, you can email me
yeah,
if more questions.
yeah, sure. I will be in touch with you.
Yes.
Sir, actually, there is one particular figure where you have shown the seismicity map of in the profile. So if you can show me that. Yeah, it's
map of
basically
whole India or Shillong?
No, just the northeast part. Little bit back, sir, where you have shown the seismicity with the depth.
Miss this one?
Yeah, this one, sir. So exactly this. No. After this, sir.
This one?
Yeah, this one. Exactly.
Yes.
Yeah, sir. Just a very intuitive question. I don't know whether my question is correct or not, but in the profile D, where you have shown the XY profile, there is a certain gap between the latitude of 24 to 27 at the depth of 50 kilometers somewhere. And if I'm not wrong, it is right beneath the Mikir Hill till the Brahmaputra fault or Brahmaputra sediment region.
Yes.
Any comment on that part?
Yes, I think in the Kopili fault zone also I have shown the section.
Yeah, exactly. It's the same.
When it is crossing that part, when it is in the section is crossing that part, as I shown the fault zone also, the upper part is active and the lower crust mantle boundary is again active. So there is a they call it no seismic zone between the upper crust and lower crust. There is some ductile part. So it is found in some places, not always everywhere, but in this part where there is a subduction zone, all along the subduction zone, you see that much gap. You are right. Your observation is right. So this part, as you say, rightly said, this is cutting across the Kopili fault Brahmaputra zone, and then is coming to this side. So here, this there is a gap between the upper it's called bimodal seismicity. I had no time. I could show you in the Himalaya also we find this Himalaya earthquakes are down to only 25 kilometers is not true. Nowadays, with telematic and digital network, we found that there is a deep erosion also, and there is a gap between the upper MHT earthquake or say plane of detachment, shallow Himalaya earthquakes and the deeper earthquakes. So these in between this even in the Bhuj area also, if I happen to talk on Bhuj interpret earthquakes anytime, I'll show you that the seismicity is bimodal. Seismicity is found in the intraplate zone as well as in the interplate zone, in the Himalaya as well as in the intraplate zone, in like Bhuj or like Kofili fault. We find first 20-25 kilometers is intensely seismically active, or 30 kilometers, or even up to 40 kilometers, and then there is a gap, and of course that is here. This gap is they are mostly subducted zone earthquakes, but here these are at the Kopili fault zone. This gap is there, so this is continuing, and then it is hollowing up. Now you can see that this deeper earthquakes is no more below this axis zone. So beyond 26 degree latitude, there is no more deeper earthquake. So this is very much clear that the subduction zone sits somewhere here at a latitude 26 degree. But as you correctly say that between 26 degree and say 25 or so, there is some gap. Yes, it is at the Brahmaputra zone over here, and this gap is also we have found in the with the local network in the Kopili fault zone also. Yes, this is bimodal seismicity. This is observed in interplate zone as well as in the intraplate zone.
Okay. Thank you, sir. Next part is regarding the northeast area. And as we know from the tectonic maps that this is the ideal place for any seismologist to be in, where you have the Himalayan subduction, then the Burma subduction, and the Syntex fault. But with the Kopali fault coming into the existence, how do you see the geodynamic model or the motion of the plates?
Oh, that is Williams mode is there. Strike slip. This is right at the strike slip motion.
Yeah.
And this is very much now in the earlier literature in the geological map, they didn't call it a Kopili fault. They call it a Kopili lineament, like they call it a Tista lineament. But now with the 2011 Sikkim earthquake, we now name it as Tista fault. Similarly, the Kopili fault is in the earlier literature is called Kopili lineament because it is the river flowing, and that was from the remote sensing data and other data, the geologist map as a Kopili lineament. But when we started doing the micro-earthquake survey in this region since 1980s, then we found that this Kopili fault or this so-called Kopili lineament is seismically much active. So in 2001 paper or so, we named it Kopili. And this Kopili fault is again, as you can see, that it is between Mikir Hills and Kopili Shillong Plateau. This fault has, in some literature, it is given that this fault has, in 2001, Nandi's book, and now he has called it Kopili fault and said that the Mikili fault and Mikir Hills and the Shillong Plateau are the part of Indian shield, and they are fragmented by the Kopili. So it is now in the literature since 2000, it's a Kopili fault that fragmented the shield part of the Shillong shield and made two parts, Mikir Hills and Shillong Plateau. And so this Kopili fault is a long fault that we have said from the long active fault that we have said from the seismic data, in the seismic data. Means we have taken it up to Bhutan earthquake. Now we are taking it up to even Manipur earthquake. So it's a long fault and produced two large earthquakes. So Kopili lineament was known in the literature before 2000, like your Tista lineament. So all lineaments are not fault, but some lineaments are, are surface expression of the fault. In interpret in Hillary earthquake, there is no fault on the map because all they can cover. There is no map fault. But we found in the river is a geomorphological evidences of a fault below 6 kilometer depth or so. And that fault that is the Kirna River, eastward river, the geomorphological evidences. So similarly, Kopili fault had some geomorphological evidences, some remote sensing evidences, and they call it lineament. And seismologists, we call it a fault. And now it is established, you can say established fact or whatever in the literature that Kopili fault is now very much known to all. Yes.
Is it connected with the MBT and the Burma subduction and the Dauki fault? Is there any evidence for that?
Yes, connected means, as I said, it is transgressing. If you can see my arrow, it is transgressing the Himalaya, and you can see the MCT is a curvilinear structure here.
Yeah, exactly.
And on the right-hand curvilinear structure, the 2009 earthquake occurred.
Okay.
The earthquake occurred by strike slip mechanism that in 2011, 2012 paper, if you see our 2012, we have said the Kopili fault is transgressing into the Himalaya, and that caused the curvilinear structure of the MCT. And this earthquake is caused by, is rather showing strike slip faulting, which is mixing with the Kopili fault. So Kopili fault could be the generator of this earthquake. Similarly, we are also arguing, this is all earth science. We all only can argue. We have not seen. So similarly, we are also arguing that the 2016 Manipur earthquake, because some people say Galot and Kundu, they say that this could be the CMF fault, that Chandrachur Mao fault.
Yeah.
We, AP Singh said that no, the rupture towards along the Kopili fault to the north, and aftershocks also along this. So Kopili fault is the source zone. So but the intersection is fine. Intersection is always a stress, stress accumulation zone. So this is, but the rupture propagated along the Kopili. So now we are saying, well, Kopili fault is from this end to this end, So this is all, earth science. We all argue like that.
Thank you, sir. Thank you very much. I'll be in for further questions. I will come to you again and contact you.
Okay, you can email me. Okay.
Yeah, sure. Thank you.
And yes, if any other questions are there, I can take up one or two more, or if not, it's fine.
Any more question?
There is one question in the chat box by Professor Guru Varan, sir.
Yes.
Can you please read it for me?
Yes. Sir, the Professor Guru Varan is asking that a very informative lecture, first of all, he said. Then it is like a layman question. How close we are to predicting a large earthquake in near future? What parameters could indicate such an impending large earthquake and the location?
Yes. This is such a younger science. As I said, geophysics is young and seismology is younger, 100 years of data. How with 100 years of data, and that too broadband only from 1996, and that too good network has come from time in 2000. So it is difficult to say the exact time, because that much data for statistical study, but still people are doing the historical earthquakes, some statistical study, like Gupta and Singh did some swarm studies. So as I said, I think I have taken up this question, rather it is of general interest for all of us, that what can make us, resilient, earthquake resilient society. And I told that no prediction, no forecast can be made till today. And even it is made, how it is practical. If I say on 10th of November, there will be an earthquake in Shillong, will you vacate Shillong city? Whole population will shift with industry and office and everything. How practical it is. So I don't think, whole world is now making earthquake resilient houses based on microzonation, whole world, and almost gave up, though prediction research should continue and should go on. But this is the most practical way of living with the nature, by making earthquake resilient houses. So say in Shillong, the people are making houses on the hill slope and multi-story building. In Sikkim, 6.9 earthquake killed so many people and destroyed all high-rise building on the slope. This thing will also happen in Shillong. Now, if you say when it is going to come, that's $1 million question. Then I would have got Nobel Prize. So it is when it will come, we don't know. But these are the vulnerable zones I told. We can identify the earthquake source zone, the generating process, and their vulnerable zones for earthquakes. So your house has to be earthquake resilient. Your house should be seismically, designed with proper code. So that is the job. I think all of us should be taken. That is the take-home message that let us, if we live in an earthquake-prone zone, which is well mapped by the seismologists, by the geophysicists, in those zones, our houses should be earthquake resilient. So that is the only way to live with the earthquakes. When it will occur with time, space, and magnitude, we cannot say. We can only say Populi fault is due for a large earthquake because already 1943 and already is of 90 years or more it is. So it is due for another magnitude 7 earthquakes. It is giving magnitude 5 earthquakes almost every month, 2 or 1 every month. 6 we get in an interval of 5-10 years. So 7 will come in its own time. We don't know when it will come. And Shillong Plateau, similar thing. So exact time we cannot say, exact date we cannot say, exact magnitude we can say only that large earthquakes may come in Populi Fault or in Shillong Plateau. These are the source zones. So rest is your awareness and making good houses to live with. It's becoming a bit lengthy. When I was in University of Tokyo in Earthquake Research Institute, I was living in the guest house. I went there as a visiting professor. And one, maybe, early in the morning, 3 o'clock or so, I found that I was in the 4th floor. I found that my bed is swinging. And I immediately could understand, yes, this must be an earthquake. And I was not panicked. I was enjoying that swing. You love that. I truly saying, I was enjoying that swing. And in the morning after, in my morning tea time, breakfast time, I found in the TV in my room that there was an earthquake of magnitude 7.5 in Japan. And I was enjoying that swing. And here, a magnitude 6 or 6.5 kills people. So in Japan, the people live with the earthquakes. We should learn to live with the earthquakes, particularly in Northeast, and particularly in the Gujarat also. So seismologists cannot tell you when, where, and what magnitude. Of course, magnitude is known. Known means, yes, from the past records, we know Bhuj has created 8.1, Bhuj has created 7.8 or 7.7, Kopili fault has created 7.4, 7.2, Shillong Plateau has created. So these are the known facts, and these are the areas where we should live with awareness. I think that is the message. Thank you so much for a very good question.
Thank you, sir. Thank you, sir. There is one more question by Dr. Shripati.
Yes, please. I can take up.
Yes, sir. Is there any method to stop an impending earthquake rather than predicting?
Pardon? Again?
Is there any method to stop an impending earthquake rather than predicting?
No. You cannot stop earthquakes. You cannot stop earthquakes because it's a nature. It's a nature geodynamics. This is the life of the earth. How can you stop its heartbeat? Immediately you are going to kill the earth or what? So it's a geodynamics. It's a natural process. We cannot stop earthquakes. And people say that, some people say somewhere, some people question me or ask me that by some artificial process, if you can drill and if you, do some explosion or something and the stress is released, then the earthquake will be stopped. The answer is no, big no. Because the large earthquake stress You cannot imagine. Let me just give an example. Say Bhuj earthquake, 7.7 earthquake occurred. Then we immediately rushed to Bhuj and recorded the aftershocks. We recorded some 6,000 events, aftershocks, magnitude some 1.5 to say 1 to, up to magnitude 5, 5.5 or so. And we calculated the energy released by the aftershocks, and we calculated the energy released by the main shock. The aftershocks, 6,000 aftershocks of magnitude, say 2, 3, 4, 5, and so on. The total stress released by these aftershocks was not even 1/10 of the magnitude 7.7 main shock. It goes in power law. Say 6 magnitude earthquake, 7 magnitude earthquake is about 1 million atom bomb. And 8 magnitude will be 30 million atom bomb. And 9 will be 300 million atom. It goes in power law. So you cannot take out the stress by your, by your manual method or by your human activity to stop a large earthquake. So this is, answer is no, but I gave you some example. The large earthquake stress is so much that it cannot be reduced by manpower manually. And as I said, Bhuj aftershock, 6,000 aftershocks could not even be 1/10 of the main shock stress energy release. Yes, I think I could explain your question. Yes.
Thank you, sir. Can we take one more question? Yeah.
Yes, please.
Yeah. Okay. Thank you, sir. This is. Hello.
Yes.
Am I audible?
Yes, Sripati, you are audible. Please go ahead.
Okay. Sir, it is also.
Yes, please read the question for me. I am there.
I just wanted to pose one more question, sir. Usually, like planetary motion. So these planetary also kind of a forces on this Earth. Whether any of these forces also cause earthquakes to occur? Planetary motion.
Yes, ma'am.
Gravity of other
Any more
planets.
questions? I am there.
Yes, sir. Dr. Shripati is trying to ask that planetary motion, gravitational force due to planetary motion, can induce earthquake, gravitational pull due to planetary motion.
Oh, yes, there are a lot of studies on this, And the people are also trying to, these astrophysical phenomena in terms of precursors also. They say that, when there is some planetary position situation changes, then the big earthquake. So there are a lot of publications on this. I'm not an expert on this, but answer is yes. The planetary motion and their position in the Earth, the way it was the tide and all things. So there is some effect. I have read some, but yes, I'm not a physicist to really explain how it does it. But yes, the answer is yes. It affects.
Thank you, sir. Maybe one last question we'll request you, sir.
Yes, please.
Yeah.
I'm sorry, Kayal Saab, with your permission, I would like
Please.
to. The Honorable Minister is online, so I have to go and attend to that. I'm
Okay.
really sorry.
Please.
Yeah,
Yes.
kindly
Okay.
permit me, sir. I will be.
Thank you.
I'll be not available for the next 10, 15 minutes, maybe. Okay. Thank you.
Yeah, thank you, sir. There is a question by Dr. Jyotima Kanujia.
Yes.
She is trying to ask that it has been argumented that Shillong Plateau is the part of Indian subcontinent and it has been broken and then moved eastward to mark its present position. What are your comments on its historical geodynamic position, and also what are your comments on the present condition at Indo-Burman subduction?
What are the comments on? Yes, Silk is a part of Indian Seal, that is in the literature. And then what is
Right.
what question?
A present condition at the Indo-Burman subduction. present condition at Indo-Burman subduction. Indo-Burmese subduction, sir. The seismic situation at Indo-Burman subduction.
Please,
Can I repeat the question, sir?
please again.
Yeah, she's trying to ask that what are your comments on the historical geodynamic position of Shillong Plateau and present condition at Indo-Burmese subduction?
I think if I understand the question, she is trying to say that Shillong Plateau is a Indian shield, part of Indian shield, and it has say dragged towards east from the Indian shield to now in this position. Possibly she is asking what will be its future or something like that with respect to subduction tectonics here, whether this Shillong Plateau will go into the subduction zone or so. If I understand the question, possibly this is the question. I know her. She is very good scientist. Yes, Jyotima, your question is very good, very interesting question. But that is, I think, with only the geological time will speak whether this whole Shillong Plateau go into the, into the subduction system or not. As you might have seen our one paper on Indian Peninsular Shield, where you have said that the Narmada Rift Zone, the big Narmada Rift Zone, the 1,000-kilometer long rift zone, I think that is the zone which has also helped the Shillong Plateau, or what should I say, helped the Shillong Plateau to come to this present situation. Anyway, that big rift zone in the middle of the Indian Shield Peninsula is a zone of future collision zone in some 50 million years time, like Himalayan collision zone. The Son Narmada Rift Zone or NSL zone would be another plate boundary, another collision zone in the middle of the Indian Shield, Peninsular India. So, and that we have tried to say from our regional tomography structure, the high velocity structure to the north of the NSL zone, rift zone, and to the south, means southern Indian Shield is lower velocity, thinner lithosphere, and it is dipping towards north. And doing some numerical modeling, we have tried this. That of course done. Modeling part was done by Kayal's group, and tomography we all did. So in 50 million years, there is a say hypothesis or whatever you say that there will be another mountain building zone in the middle of the Indian Shield or Indian Peninsular area. Similarly, your question is, if I correlate with that type of question, whether the Shillong Plateau future will be in the subducted Indian plate below the Indo-Burma ranges. Maybe you are the one of the brightest geophysicists, and you can do the numerical modeling, and you can see, in 50 million years or 100 million years time, whether this Indian Shield will be part of the subduction zone. Today it is intraplate zone away from the subduction structure, but whether it will be also part of the subduction structure, that part, I think you can draw the best, not answer, you can draw the best research on that. Thank you so much for a very nice question, Jyotima. Thank you so much.
Thank you, sir. If there are no more questions, then on behalf of IIG Director and my colleagues, I again extend our sincere gratitude to Professor Kayal, sir, for accepting our invitation and delivering today's lecture. This lecture had been scheduled as part of Azadi ka Amrit Mahotsavat, celebrating 75 years of India's independence. I am grateful to our director, sir, Professor D.S. Ramesh, for providing all encouragement and necessary support for this talk series. I would like to thank IIG's Academic Program Committee for encouraging us to initiate this series. Many thanks to IIG's Science Outreach Committee, Rajbhasha Committee, and Computer Section for all the support and help. Thanks to Mahindra, Doifad, and Tabis for making possible the YouTube live of this talk in a very short notice. I think first time we are going on air in YouTube actually. So thank you so much to both of you. I'm grateful to my SGRC colleagues for their extensive support in organizing this lecture. Last but not least, of course, audience outside from IIG. Thank you very much for attending today's lecture and hope to see you again during the next talk. With this, I wish you all a very great day ahead. Take care and stay safe all. Thank you. Thank you, sir.
Thank you, ma'am. Thank you so much for your kind invitation. I really enjoyed and
Thank you,
all
sir.
the questions. It was wonderful. Thank you so much, ma'am. Thank you. Thank you all. Thank all participants for their, patience. Thank you all.
Thank you, sir. Mahindraji, we can close today's meeting. Thank you all.
Thank you, ma'am. I'm now closing. Thank you all.
Sure,
Thank you,
sir.
ma'am.
Thank you, sir.
Thank you. Thank you all. Thank you so much.